All right, separable differential equations. I need to go over this a bit better. An equation with a function and one of its derivatives, that's what a definition for a differential equation is. The highest derivative in the equation is called the order of the equation. So when we look at this, this has a second derivative, so it's order 2. Over here has a third derivative, so it is order 3. Separable differential equations, first order differential equations that can be written in the form of dy dx equals something like g of x times f of y, or you could write dy dx, so I'll just put it on this one, g of x over h of y, and the only reason I'm writing it like that is so I can rewrite it in the next line. We have, if we separate them, we can multiply both sides by h of y, so we'll have h of y dy equals g of x dx. So what we have now done is separated the variables. We have all the y's on one side, we have all the x's on the other side, and now we can integrate. And that's the idea. So important. A solution for a differential equation is you have to know this, a differentiable function on an open interval that contains the initial value or our initial condition. So another way to say this, i.e., the function must be differentiable, and you want to think about what that's meaning, on the largest open interval that contains the initial condition. So we're talking about a differentiable function. So if it's not differentiable at a point, then that's not going to be a part of its domain. So it needs to be a differentiable function on an open interval that contains the initial condition. Let's take a look at this. This is a type of question you just have to know. It's very common. It's very straightforward once you learn the basics of doing it. So the rate of change, what is that talking about? The derivative of a function. So we'll have dy dx is proportional, so some constant k, to the function y. So we've written a differential equation. This is an order 1. This is a separable differential equation. And now we're going to solve it using this method of separable differential equation. So we'll move y's on one side. We have dy over y equals k dx. Integrate. We have ln of the absolute value of y equals kx. You have a constant on both sides. We move it to one side and we'll just write c once. We get absolute value of y equals e to the k plus c. We can rewrite that as e to the kx e to the c using our exponent rules. We're just going backwards than what we normally do. And now we have, get rid of the absolute value. We have y equals plus or minus. I'm going to move that c, e to the c in the front, e to the k. Now what we're going to do is get rid of this constant, plus or minus. We don't know what it's going to be. We don't know if it's positive or negative. That's going to depend on the initial condition. The way we're going to realize, or what we're going to do with that, is we will let that be some constant. So I'm going to change this, and I'm going to call these C1s. So we'll say let C equal plus or minus e to the C1, and we get y equals c e to the k. And it's always going to end up looking like that, but what you have to be able to do is start off with the words in this sentence and then come up with this equation. If you know that, you can jump to there, but you also have to know how to derive it. Let's look at a couple examples that will help us illustrate what's going on. We have, one of the things we should recognize right away is if y equals 0, is this thing differentiable? No, because this has a negative exponent there. So we know y cannot be 0. Now let's go ahead and separate it. We'll have y squared dy equals 1/3 dx. If you realize you can do this and this will work, but if you realize that this would be better to put with that y squared, then you can go ahead and it'll save us a little bit as we're going on. Because what's the antiderivative of 3y squared? That's just y cubed. So we have y cubed equals x plus c. We have our initial condition, 1, 1, so we have 1 equals 1 plus c. In this case, c is 0, and we get y cubed equals x, or in other words, y equals x to the 1/3. But we know that y cannot be 0. Since y cannot be 0, we're looking at x cannot be 0, because we're looking at the domain here. So if x cannot be 0, then we can just look at a quick number line, or just think about it here. We have 0, we have x equals 1. So that's saying we're dealing with this part. So my solution is going to be y equals x to the 1/3, and the domain will be x is greater than 0. Let's look at the second example. Over here we have an initial condition of y of 1 equals 0. We're going to separate our variables. We'll have dy over the square root of 1 minus y squared equals dx. Go ahead and integrate. You know that this is just inverse sine of y equals x plus c. And then plug in our value. Inverse sine of 0 equals 1 plus c. Inverse sine of 0 is 0. So c equals -1. So we have this equation, inverse sine of y equals x minus y. Now, what do we know about the inverse sine of y? This is a function, so the inverse sine of y is bounded by -pi/2 and pi/2. But inverse sine of y is equal x minus 1, so that means we have this relationship. We can substitute x minus 1, solve for x, so now x is bounded by pi/2 plus 1, or 1 plus pi/2, it doesn't matter, 1 minus pi/2. So that is going to be our domain. We're going to solve the equation for y, so y equals the sine of x minus 1. So our complete solution will be this. We have a differentiable function on the largest open interval that contains that initial condition. Let's look at the next one. We have again y cannot be 0, because then the function would not be differentiable. One thing to note, I could point out over here, is when we look at this, dy dx is always greater than or equal to 0. And so when we're finding our domain of the function, it should be agreeing with that. All right, over here, let's separate the variables. So we have y to the 4th dy equals t to the 4th dt. Let's integrate both sides. The antiderivative of y to the 4th would be 1/5 y to the 5th equals 1/5 t to the 5th plus some constant c. We can plug in our initial condition and we'll get 3 to the 5th divided by 5 equals 0 plus c. So in other words, c is 3 to the 5th divided by 5. Now, did we have to plug it in immediately at this stage? No, we could have waited and gotten rid of the 1/5, and we could have made a new constant here, c. It's not a big deal. Now we have the equation y to the 5th over 5 equals t to the 5th over 5 plus 3 to the 5th over 5. Let's get rid of all the 5s. We get y to the 5th equals t to the 5th plus 3 to the 5th. Now we have to say what to figure out our domain, but we know y can't be 0. So if y can't be 0, we're going to come over here and say, hey, y can't be 0, so we get 0 cannot equal t to the 5th plus 3 to the 5th. And so we'll get t equals, or can't equal, negative 3. So on this, if we're looking at here, where y cannot be 0, we can't, that means on our x numbers, or our t numbers here, t cannot be negative 3. And we look at our initial condition, where does 0 lie? 0 lies over here. So what will our domain be? Our domain will then end up being t is greater than negative 3. So our final solution will be y equals t to the 5th plus 3 to the 5th, all raised to the 1/5, with the domain of t greater than negative 3. And that is it for the separable differential equations. Again, I want to emphasize that first sentence that we were talking about. We're talking about a solution to a differential equation is a differentiable function on an open interval that contains the initial condition, or the function must be differentiable on the largest open interval that contains that initial condition.